Hello. Today I'm going to talk to you about modeling the stress dependence of rock properties. I'm going to talk about a framework for a unified rock physics model. I'm Arthur Chang. I'm with the Sustainability Geophysics Project from the National University of Singapore. First, let's talk about the pressure behavior of rocks. It's common knowledge and a lot of laboratory data that shows that P-wave velocity and S-wave velocity increases with differential pressure, which is the confining minus the pore pressure. This particular data set is from Han et al. In 2011. Now, Han also recorded resistivity at the same time on the same sample, core sample, simultaneously. And what you see here is the resistivity follows the same trend, increasing in resistivity with differential pressure. Furthermore, the dependence can be shown to be an exponential dependence on pressure. So, altogether, Han collected over 60 different samples, which are shown here. Each color sample, one sample, measures 6 different pressures. So here, 1, 2, 3, 4, 5, 6. And one of the general trends you see is for rocks with low resistivity and low VP, the codependent is slow. The slope of the dependence is small. Whereas for the rocks with high velocities and high resistivity, the pressure dependence is steeper. So we have seen relationships between velocity and resistivity in various forms, but the pressure dependence of these two has never been adequately modeled. How do we model together the elastic and electrical property of rock as a function of pressure, so that we can mimic the data we've seen in Han's work? Now, if you use the classical models, there are 2 types. One is based on contacts of the grains. It's limited in modeling the pressure dependence. The other one is modeling the ellipsoidal inclusions. Because these inclusions are usually modeled as isolated inclusions, it cannot model resistively easily. The contact model also doesn't say much about the pathway in the pore space. So we are proposing a unified model using a rough surface model. Now, we are not the first one to think about this. There have been a number of rough surface models. Walsh and Rosenbach, Brown and Schultz, Ganges, Beck-Mills, and others. Most of it focused on the flow and static deformation, and not so much work has been done on the dynamic elastic properties. Here we focus on integrating electromagnetic and dynamic elastic behavior into a unified model as a function of pressure. By specifying the statistical distribution of the roughness of the fracture, we can deterministically calculate resistivity and velocity both as a function of pressure. This simulation work done by Joseph Ma at NUS. So Steve Brown proposed this rough surface model. Basically, you have upper and lower surface with opening. Equivalently, you can just describe one surface with a flat surface on either the top or the bottom. The beauty of a rough surface model is there's an implicit linkage between fluid flow or electrical flow also and elastic properties. The contact areas give you the stiffness of the rough surface. The non-contact area gives you the compliance of the surface. And the open and connected pores tells you something about fluid flow and conductivity. With pressure, it increases the contact points, it reduces the non-contact surface area, and reduces the aperture height. So we do simulation based on a single rough fracture model. There are three parameters that characterize an initial fracture aperture distributions, as shown in this figure. First is the autocorrelation length lambda. Second is the standard deviation of the first contact aperture sigma. And third is the mean aperture h. What does pressure do? Pressure P leads to a uniform compression of the displacement delta. So the first thing we need to do is get a relationship of the applied pressure with delta. And this relationship depends on the statistical properties of the rough surface. Now, there have been work on this for various people. The one that we're going to use is based on Giroux in 1968 and Unger and Mies in 1993. This gives you the static compression modulus. So here you have an effective pressure and the corresponding compression displacement. The higher the pressure, the more the displacement. So now let's see how that happens. If we start at each initial rough surface like so, being compressed by a flat surface, so as we compress, applies more and more pressure here, the white spots here means the two surfaces are in contact. And the opening, aperture height decreases, getting darker and darker, and the distinct flow path appears. Flow simulation. Using a direct current model by 2D Ohm's law. Current equal to a resistance per term times the gradient of the voltage. There are two terms. There's a fluid conductance term and a rock conductance term. So the electrical resistance evaluated from the total outgoing current is given by this. Resistance equals to gradient of the applied pressure and the measured current. And for the effective resistivity of the rock is just a geometric term times the resistance. So let's look at what it looks like in our simulation. First, we show you the electrical potential as a function of pressure. And you notice distinctly the electrical potential becomes non-uniform with pressure. You get higher and higher pressure, you get distortion in the electrical potential field. And what about selected electrical current flow path? As you apply the pressure, the flow path distorts. Originally, you can flow pretty much everywhere, but as you apply the pressure higher and higher, distinct flow path appears, like so. In the end, that leads to a resistivity versus effective pressure plot looking something like this, which is shows that the drastic increase at the low pressure and more gradual increase at the high pressures. We're going to talk about the velocity modeling part. Conventional modeling uses the contact areas and apply the Hertzsprung type of models to calculate the increase in the contact stiffness as the number and area of contact increases with pressure. Now, we take an opposite approach or complementary approach and model the non-contact area using the classical wash penny-shaped crack and crack density approach. Okay. Now, you can argue this basis doesn't quite look like a penny-shaped crack. With that, so this is an approximation. If we take the fracture surface as 1, then the crack density is just a fraction of the surface not in contact. And with that, we can use any number of crack density-based model to calculate the velocity. Here we use the Chang model, calculating the vertical stiffness C33 and C44 with the Pade approximation for large crack density. So here we show you the crack density calculated from the non-contact yellow area as you increase the applied pressure. Initially, there's a lot of non-contact area, high crack density. As you apply pressure, there's less and less cracks, and the cracks kind of close up. It resulted in a velocity as a function of pressure looking like this. The velocity increases sharply at low pressure or gradually at high pressure. So now we have the velocity as a function of pressure and the resistivity as a function of pressure. We can plot them together. So we got this velocity resistivity cross plot. And it's actually a very straight line as a function of different pressure. You see the different color here, which is quite interesting. Resistivity depends on the height of the aperture. Velocity depends on the non-contact area. This specific relationship depends on the statistical description of the roughness of the fracture. So I'll bring back the lab data from Han, saying the 60-odd lab measured resistivity versus velocity as a function of pressure, and see whether we can at least mimic these behavior. And here it is. Each color stands for one sample, simulated at 8 to 60 megapascal, 3 different sigmas, constant aspect ratio of 0.01. So it shows you basically the same trend as we have seen before. So I believe we are on the right track. So what we're seeing is a stress dependence in the integral part of rock physics. It holds the key to understanding the different physical property in a unified manner. What we just presented is just a framework with first-order approximations for the calculation of the properties and needs much more development. Anisotropy can be fit into this framework. And 2D to 3D is possible with the older fabric tensor approach. Thank you. We welcome your feedback and questions. You can contact me at Arthur C. Chang, Arthur Chang at alum www.mit.edu.